So when we're thinking about electrolytes, we have to think about the fact that they dissociate and also that they have extra particles. And when we're thinking about activities, we have some sort of wrinkles to this by the fact that we can't have a positive ion without a negative ion. So we sort of have to think about electrolytes coming together in pairs, right? Or more than two substances even. But let's say we have a cation and an anion that are going to dissolve in a solution. We'll have a certain number of positive and negative species that are going to dissolve when our species reach solution. We have to think of these together. All right, and they'll have some charge on them. And we have our positive ions and our negative ions. Oh, that should not be a Z, that should be an A. My notes are wrong here. A Z minus. All right, so we're going to have both positive and negative ions present. And what we can think of here is that nu plus and nu minus, these are the number of positive ions, number of cations that'll form per mole of our salt, and nu minus is the number of negative ions, number of anions per mole. And these will just come from the formula units for your salt. Now we have to define our activity in some way that accounts for both of these because we can't define one by itself. So we say, okay, activity of our solute here, we define it as A plus minus raised to the nu, where nu is equal to nu plus plus nu minus, right? It's the total number of things you get. We've seen this value before in the last video when we were thinking about colligative properties. And then this is equal to the activity of our positive ion raised to the nu plus times the activity of our negative ion raised to the nu minus. Now, obviously, we can't separate these out. So what we find instead is what we call a mean activity coefficient. And we can define these activities in terms of molarity or molality, however we want to do it. So our mean activity coefficient is defined as, mean ionic concentration, M plus minus in terms of molality, but we can also do this in terms of molarity raised to the nu is equal to M plus raised to the nu plus, M minus raised to the nu minus. And we define a mean activity coefficient, gamma plus minus raised to the nu, is equal to gamma plus, gamma minus, nu minus. Okay, so overall, after all this, we define our activity for our solute as this mean activity, which is equal to our mean activity coefficient times our mean concentration. Okay, this allows us to sort of consider both positive and negative ions at the same time. Now, the reason we have to define all of this is because we need a way to find activity coefficients. Now, we can, of course, use the method that we talked about at the beginning of the chapter for non-electrolytes. We can use that with electrolytes as well, where we measure pressures of our solvent as we add electrolytes. But there's also an expression that was developed, a theoretical expression to find activity coefficients of electrolytes. And this is known as Debye-Huckel theory because it was developed by Debye and Huckel. Oh. All right. And we will not go through the derivation of this expression. We will instead look at the consequences of it. And we will look at that in the next video.